Hello again. Let's continue with the second session in our training today. Let's start to do an efficient parallel reduction algorithm in CUDA, which was proposed by Mark Harris from the NVIDIA Developer Technology. Uh, and this is the link of the document, and you can also download it from this website. Okay, let's start with the idea of parallel reduction, and he uses tree-based approach for each thread block. So for each thread block, a tree-based approach will be used to compute to reduce the data. So and we need too many blocks when the array size is very large, for example 2 over 20, and when we want to keep all streaming multiprocessors on the GPU busy. So we need many blocks in such stations, and each block does a reduction over each portion of the array and produce a single output. Here, in this figure, this is an illustration of a thread block, and thread block does reduction over the portion of the array and produce a single output. And how we combine the outputs of each block? So we need to combine them. So in order to combine the outputs of blocks, we need a synchronization mechanism between the blocks. So when a block completes reduction, it needs to wait the remaining ones to complete their reductions and obtain their outputs. Then we need to combine them. So a recursive processes should follow to obtain output, but in CUDA, the synchronization between the threads in the same block is possible. Remember from the yesterday, the threads in the block, same block, can synchronization with synthreads instruction. There's an instruction for synchronization with the threads between the threads in the same block. However, the threads in different blocks cannot be synchronized each other. So the blocks cannot synchronize each other. Why? Because the synchronization of the blocks is an expensive process for the GPUs, and in fact, CUDA forces the programmers to create fewer blocks, which may reduce the overall efficiency. So how can we synchronize the blocks each other? So using multiple kernels is a good solution. There is an implicit barrier between the kernel launch. So when we run kernels consecutively, there is an implicit barrier. So the following block kernel must wait before the previous kernel finish its execution. On the other hand, we can use multiple kernels because the kernel launch has low overhead. Here is an illustration. We call two kernels here. The first one is given with green. The second kernel run is given with blue. In the first kernel run, you see that 8 blocks runs here. 8 blocks. As you see that each block performs a reduction. There are three based approaches here, and each block performs deduction over the some portion of the data, and they produced a single output. Here, 8 single output are produced, and we need to combine them and to get the overall output. And we do this one in the second kernel run with the blue one. So in the blue one, we combine the outputs of the blocks in the previous kernel run. Then we do the same reduction again with one block, so and we get the overall output. The code of both kernels is same, so we can launch them recursively. The code is same. And what is our goal in efficient reduction algorithm? Our goal is to try achieve high bandwidth because the reduction has low arithmetic cost. So our main target is to achieve high bandwidth. And in this example, here is used NVIDIA G80 board, and it has 36 gigabit per second memory bandwidth. So let's start with the first approach. He tried 7 different approach, and I will show them one by one. The first one here, the intelligent addressing. Let's look at the kernel here. This is the kernel, reduced zero kernel. It has an input data and output data, and it creates a shared memory here. And the TID variable is the local thread ID inside the block, and variable I is the global thread ID, and each thread reads the data from global memory by using the global thread ID and save it to the shared memory. And this is the sync threads to synchronize the thread in the same block. So the threads in the block are synchronized by use this instruction sync threads. So when all of the threads in the block read the data from global memory and save them to the shared memory, we continue with the for loop. And each thread in the block executes this for loop. And at each iteration of the for loop, there is a sync threads instruction again. So all the threads in the block waits in this position until all of the threads in the block execute the previous kernels. This is if clause and for loop. So at each iteration of for loop, there is a synchronization and reduction, tree-based reduction performs through with this for loop. So this for loop does tree-based reduction for us. So the variable of for loop starts from 1 up to the number of threads in the block and increase the variable by multiplying it as 2. So s will be the power of 2. And we are using local thread ID, a modulo operation, and 2s here. S is the variable of for loop, and if it is 0, do the summation between the two memory location. So for the if condition, the threads whose local ID is 0 or multiple of 2s satisfy this rule and performs the summation operation. I will show you the illustration of this operation on the following slide. And once the reduction completes, that means once the for loop finish execution, then the result of the block, the result of which is kept in the first element of shared data, and we transfer that data to the corresponding global output data by using the block ID. So GO data corresponds to the output of each block. So according to the block ID, we set the output of block to this global array, and the first thread performs this operation. Okay, I will show you the behavior of this for loop now. Here, the for loop has this operation. In the first iteration, thread 0 sum its current data location, and the consecutive one read them and sum them and save it to the again. The memory location is thread ID, and second thread read both elements and write them to the memory location with index is same with the thread local ID, and then the fourth thread, the fifth thread with 4, and seventh thread to this one, and so on in the first iteration of for loop. In the second iteration of for loop, stride will be 2. What that means, stride is s here, s. In the second iteration, s will be 2. In the third iteration, s will be 4. And in the fourth iteration, s will be 8. And this for loop iterates 4 times, as you see, 1, 2, 3, 4. And in the second iteration, thread 0, thread 4, thread 8, and thread 12 are active and do the summations. And in the third iteration, thread 0 and thread 8 are active and do the operations. And in the last iteration of the loop, thread 0 is active and do the summation and get the overall output of the corresponding block. So these operations are performed in each block. But there are some problems in this approach. What are the problems? The first problem is with this strided approach, there are highly divergent verbs, and they so they are very inefficient for us. Here, let's look at it again. On thread 0, thread 2, thread 4 are active, but thread 1, thread 3, thread 5, they are in idle. Again, here, thread 0, thread 4, thread 8, thread 12 are active, but their neighbors are in either position. So this causes verb divergence here. And again, the other problem is modulo operator is a very inefficient operator. So in the second approach, he overcome these problems. Let's look at the execution time of the first approach. It is 8 milliseconds, and this is 2 gigabit per second bandwidth. And remember that the block size is 128 threads for all kernel launch. Okay, let's look at the second approach. In this approach, he eliminate the modulo operator and eliminate the word divergence problem by using strided index and non-divergent branch here. Here there's a strided index. This index is based on S and local thread ID. If index is less than the number of threads in the block, do this operation. So with this strided index operation, the threads, the consecutive threads does the previous operation. Here in this one, uh, not the consecutive ones are executed here, 0, 4, 8, 12. In the second approach, here the consecutive threads are active here. Thread 0, thread 1, thread 2, thread 3, thread 4, thread 5. So the threads in the same warp are active. So we eliminate warp divergence. Again, in the second iteration, thread 0, thread 1, thread 2, thread 3 are active. So we eliminate warp divergence, and by using strided index, we eliminate here modular operation. Now, but in this approach, a new problem occurred, shared memory bank conflicts. But this problem is valid for first generation hardwares. And in this hardware, we do not face, in this example, we do not face shared memory conflicts. So, how he overcame this problem is he forced that the consecutive threads are access to the consecutive memory locations, like this one. Access the consecutive threads accesses to the consecutive memory locations. Here again, when reading this portion of data, they access consecutively. So overcome this bank conflict problem. Sorry. The performance of second kernel is here 3.4 millisecond, and this cumulative speed up is 2.32 in the second kernel. In the second kernel, we eliminate warp divergence and problem on modular at face with shared memory bank complex, but valid for the first generation hardwares. Here, in this third approach, it is eliminated by forcing the threads in the warp access to the consecutive elements of the device memory, and so on. How it is achieved here? Just replacing the if condition and strided index here with thread ID based indexing here. Now thread ID based indexing, and stride is the current value of loop variable for the third approach. Sorry. For this approach, again, strided index is eliminated, and thread-based indexing is used in if condition, and as the initial value of s will be the half of the number of threads in the block until s is greater than 0, and s is decreased by dividing it to, and so on. So the performance of kernel 3 is here. Execution time is 1.7 millisecond, and step speed up is 2x, and cumulative speed up is 4.68 with kernel 3. But in here, there is another problem. The problem is half of the threads are idle in the first iteration of the loop. Since S is here started for S is set to half of the number of threads in the block, so only half of the threads in the block satisfy the if block. So the second half of the threads in the block are idle in the first iteration. So this wastes the resources of the GPU. This is very important. So how can we overcome that problem? If we halve the number of blocks and if we replace a single load with two loads on first edge of reduction, we can eliminate. This is our current kernel. Here we only do a load operation, does a load operation here, but in the new approach, we have the number of blocks and now each thread performs two load, first data and traded data, and sum them here at the beginning and save it to the shared memory. Before for loop starts, two loads and first add operation performs here. So in order to get the global thread ID, now we must times block dimension with 2 because we have the number of threads, so we must times it by 2 in order to get the proper global ID for a thread. So this is the solution of third approach, and the execution time of fourth approach is 0.9 millisecond, and the step speed up is 1.78, and cumulative speed up is 8.34x. Now, so far, when we look at the bandwidth, we achieve up to 17 gigabit per second. But remember that the board G6 and G80, G80 uh, has a bandwidth of 86 gigabit per second. So when we compare it with the capacity of our GPU, 17 is very low. So how can we increase this bandwidth? Now, there are some other overhead that cause very low bandwidth. One of them is loop overhead. Loop overhead. I'm sorry. Uh, Loop overhead occurs in these approaches. So what that means, at each iteration of the for loop, the number of active threads reduces. When stride s is smaller than 31, only one verb is active. So that means when here when s when s is smaller than 31, there are 6 iterations left. This one. Okay, there are 6 iterations left, and only one verb will be active. And since only one verb is active, we don't need to synchronize the threads in the verb by using sync threads function, because this is used for the threads across the block, inside the block, the threads inside the blocks. But for the threads in a verb, we don't need to use sync threads function, and we don't need to synchronize the threads in a verb explicitly because all the threads in the verb execute the same instruction. So this is also wasteful. We need to eliminate such kind of overheads. And when s is smaller than 32, we don't need to evaluate last 6 iteration for the remaining verbs. Since the remaining verbs will be idle, no need to evaluate the last 6 iteration inside the for loop. So what can we do? We can unroll the last 6 iteration of the loop. Here we can unroll it, and we define a device function here, device function that is called inside the kernel. Name is verb reduce, and we have an input data and the local thread ID. We must use volatile for the input data. This is shared memory data. We must use because using volatile, disabling optimizations for that memory location, such as caching. So in order to ensure that all of the threads in the world access to the latest value of the shared memory, we must use volatile here. So we can ensure that they access to the latest value of that shared memory. And then since we unroll the last 6 iteration of for loop here, so we can replace this rule. We can replace s greater than 0 with s greater than 32. Okay, so we unroll the last 6 iteration, and then the for loop terminates, and only a single verb will be active, and the threads in that verb, the thread local ID, whose ID is smaller than 32, call this verb reduce device function in order to evaluate the last 6 iteration of the for loop. So with this approach, the execution time of fifth kernel is 0.5 millisecond, and we achieve 1.8 speed up, and we achieve 15 x cumulative speed up with kernel 5. So the question is, can we unroll all of the iterations of the loop? Can we unroll all of them? Yes, it's possible. Why? Since the possible values of block size are fixed and known, we know that the block size can be at most 1024. So we know it at compile time. So we can completely unroll the iteration of the for loop. How can we do it? By using C++ templates, we can completely unroll the number of iterations of the loop. Here, this is a prototype of template kernel. Here, the block size is used for function template parameter. Let's look at this approach. We have already unrolled the last 6th iteration. Again, here we can also unroll it here by using if condition. If block size is greater than 512, do this one. If it is greater than 256, do this one. If it is greater than 128, do this one, and so on. These are the iterations of the for loop. And of course, here the maximum one is 512, but this is for the older hardwares. For the newer GPUs, the maximum block size is 1024. Don't forget. And the red ones here are evaluated at compile time. Depending on the block size, the red ones are evaluated and the final code will be generated at compile time. So as you see that we completely unroll the iteration of the for loop. How can we call it here? By using switch case, the number of threads in the block as the given parameter of switch case, then according to the number of threads, we call appropriate kernel here, as you see. Of course, the maximum one must be 124 for the newer GPUs. So we have in possible 11 possible block size. So we have 11 keys here. So when we check the performance of uh, 6 approach, here the total execution time is 0.3 millisecond and step speed up is 1.4 and the cumulative speed up is 21.16. As you see that bandwidth increases with these approaches. Just a minute. Okay. Before the last approach, I would like to show you the complexities. The step complexity is O log n, and the work complexity is O n. Time complexity is log n. Processor time complexity is n log n of this approach. And for this last approach, algorithm cascading is used. What they mean? It means the combining sequential and parallel part of the algorithm. Sequential operation and parallel reduction operations will be evaluated at the same time. Which one are the sequential operations? Which one are parallel reduction? So performing loading the data global memory and summing them uh, sequentially summing them are sequential operations, and the for loop then the unroll one are tree based reductions, and they are executed in parallel. So the parallel approach is the tree based reduction. So we will combine both sequential and parallel parts of reduction together to get a mixed one here. This is the last approach. This one, this load and add two of elements here and save it to the shared memory is a sequential operation. So we can do this as many times or for any number of elements. We can repeat this operation again and again. So here, by using while loop here, we can do this load and adding operations uh, as many iterations as wish here. So again, as you see that the loading from global data and summing through the same shared memory, and this is n is the condition in while loop. At the beginning, in the previous examples, or here, if the block dimension is the regular one, this loop iterates once. If you want to increase the number of iterations of the while loop, we need to decrease the number of threads in a block. Here, if we decrease the number of threads in a block, the number of iterations in while loop increases. So the sequential part increases, and the level of tree also decreases. If we reduce the block size, the level of tree decreases, the number of iteration of while loop increases. So we should maintain the balance between the level of tree and the iteration of the for loop. There is a balance here between the level of tree and iteration of the for loop. So you can decide the number of iterations of while loop by decreasing the number of threads in the block, and you can investigate it, and you can find the proper number of threads for a block for your application by doing trial and experience approach. So this is the last approach, and the execution time of last approach is 0.2, and the current step speedup is 1.42, and the cumulative speedup is 30x, and as you see that the bandwidth is 62 gigabit per second. It's very good output for us, and this is the overall optimized kernel. Here, this is the unrunning of last 6 iteration. As you see that we define while for the loading operation and summation for the sequential part. And for the tree-based approach, we unroll all of the iterations here by using if structures. So we unroll the for loop completely, and this is our final optimized kernel. And this is the performance comparison for different number of data, and the execution time here, as you see that the last approach 7 is the best execution time. And these are the references. Okay. These are the references. Any questions so far? I face some problem and I cannot read the chat panel or question and answer panel clearly because of some problems in Ubuntu. Please write your questions to the question and answer section.
I think there is no question in the Q&A box.
Okay.
But there is a question in the chat box. Can we use CUDA parallelization and any CPU parallelization at the same calculation? Is this logical? And can we get extra speed up?
Of course, there are mixed approach. For example, you can run your CUDA code along with MPI or OpenMP. So you can benefit both CPU parallelization and GPU parallelization. Yes, it's possible.
Okay, I think there is no other question.
Okay, thank you very much. Okay, let's continue with the next session. Okay, but how can this this is okay. Okay, now let's continue with the next session, and in this session I will show some libraries such as Truss Library, Coda Library, and I will compare the three parallel reduction algorithms, one for the reduced function in Truss Library, the second one is the reduced function Coda Library, and the third one is the parallel reduction algorithm of Mark Harris that I taught you in the previous session. Then I will mention to some remaining issues and important remaining issues such as use of CUDA map set properly or initializing cost of the states of random number generators. It is also important issue, I think. And the L1 cache used in Tesla K40 board. And remember, this is a specification of the board that I used in my experiments.
We can see your slides.
Sorry?
We can see your slides.
Didn't I share it?
I guess no.
Now
we see the screen, but we can't see your slides. Can you make it full screen?
No, interesting. Just a minute. Even if I started share screen, it's fine. Can you read it now?
Yes, it can be seen. Thank you.
Okay, and now the next topic is the libraries and remaining issues, and this is the specification of the board I used in my experiments. Okay, and first I will show you Truss Library and Coda Library, then I will compare the three parallel reduction algorithms. The one is the reduced function of Truss Library, the second one is the Coda Library, the reduced function of Coda Library, and the third one is the parallel reduction algorithm proposed by Mark Harris, as I told you in the previous session. And then I will mention to some important remaining issues, such as the use of CUDA map set properly, and the initialization cost of the states of random number generators is also important issue, and L1 cache used in Tesla K40 board. Let's start with Truss Library. It is a CUDA C++ template library, and it performs data parallel operations such as scan, sort, or reduce operations. And these are the website of Truss Library. You can get more detailed information through this website. And let's start with the concepts of trust. Trust has two kinds of vectors. Host vector, this is used for memory, host memory, creating host memory. and the second one is device vector to store the data in the device memory of the GPU. The host memory is allocated as below here. We create an host memory by using host vector, typing by entering the typing here, and the number of elements of the array in the memory. It has 4 elements, and we can initialize it directly as in the regular arrays. For example, here we can allocate it directly as in the regular arrays. We can also here create a device memory, allocate a device memory here by using device vector of Truss, and we can initialize it when creating it. We can initialize by using the host array, host vector. Also, we can copy host vector to another host vector or a device vector to another device vector in Truss Library. Okay, let's examine this example code. These are the corresponding Truss libraries that was here. You can include them as with the regular libraries of CUDA. Let's look at the some functions of Truss here. We are creating a device array with 10 elements here. The first parameter is the number of elements, and the second parameter is the initial value of these elements. We set all of them 9. We create 10 elements and set 9 to all of them. By calling fill function, we can fill the given array and the range of a given array with the given value 10 here. So the starting index is the beginning of the array. The last index is the fifth elements of the array here. So we set 10. So we set 10 to the first 5 elements of the array D here. And in here we create a host memory H, and we initialize it the values of device memory here. The starting position is the beginning of D, and the last element is the third element of D. So first 3 elements, the values of the first 3 elements of D will be copied to the H, host array H, and the size of the H will be 3. Okay, and their values are the values of the first 3 elements of D, which is 10, right? Yes, 10 at this point. Then there is another here, a function, sequence function here. So this set the elements of the given array to the values starting from 0 up to the given index. So the elements are ordered in the sequence. So starting from the starting index is the beginning of H, and the last index is the last elements of the H. So since H has 3 elements, the values 0, 1, and 2 will be set to the H consecutively, each element of H consecutively. Now the first value of H is 0, second one is 1, and the third one is 2. Then here a copy function is called. So the which data will be copied is determined in the first two parameters. The first element, the index of the first element, is the first element of H, and the last element will be the last element of H. They are copied to the D, starting from the first element of D here. They will be copied to the D, starting from the first element of D. So since D is first, I'm sorry, yes, okay, the values of H will be copied to the D starting from the first element. Yes, it is true. So the first three elements of the D will be 0, 1, 2. And the others here, 10, 10, are copied in fill function. And the remaining ones are 9, are copied in the first line here, by creating the device vector. And the values of H is 0, 1, 2. It is copied here with the sequence function. Okay. We can also use a row pointer. What is row pointer? A regular pointer in C++ and CUDA. So we can use that pointers in a truss function. How can we do it? This is our regular pointer, and we allocate a memory for it here. How can we use it? This one. This is our row pointer. By using this command, this one, we can use row pointer in a truss function. So this is the name of the new pointer. So this will be used inside the truss function, as you see. So it keeps this one, keeps the address of row pointer, and we can use that address inside the truss function. And reverse is also possible. So we can extract row pointer from truss device pointer. Okay, this is our truss device pointer. We allocate a memory location for it by using this command, this function. We can extract the row pointer of this device truss pointer here. Then we set the address of it to our row pointer, as you see. Now we can use it. We can use that address in our regular pointers. Okay, there are some algorithms in Truss Library. The first one is transformations. Transformations is the first algorithm. It applies an operation to each element in a set of input range and store the result in a destination range. So we apply an operation to each element in the range and store the result in the destination range. Let's look at some functions in transformation. Here we create three device vector by using truss device vector function here. All of them has 10 elements. Then we set the value of x as the sequence of numbers starting from 0 to 9. So these are set to x consecutively. And there's a transform function, as you see. So the values of y, the values of y will be the negation of each element of x here. The starting index is the first element of x, the end index is the last element of x, and the starting position of y is the first element of y. So the negation of each element of x is copied to y. And this, the third parameter, tells us that the operation is negation operation. Okay, in transform function. And there is a fill function. So to the given range, the tree will set to the given range of z. So the first element of z and the last element of z were given as the parameters. So all of the values of z will be 3 after fill operation. We have now another transform operation. So it gives us the modulus operation here. We tell that with the fourth parameter, there will be a modulus operation. So what is the operation? Operation is y is equal to x modulus z. So here, the starting elements of y is the beginning of y, the starting index of z is the beginning of z, and the values of the x in the range started from the first element up to the last element. So this formula applied for each data in x by using z. And replace operation here, this is replace 2's with 5's in the given range. Okay, so in all of the elements of y, the 2's are replaced with 5's. And the last one is the copy operation. So this is used for printing y. How we can print here, which values, the starting element, the first element up to the last element of y will be printed to the screen. How? Here we define O stream iterator, and we define cout, and at each line we execute new line operator. So this will print this one, as you see. So the copy operation is printed. It prints the value of current value of y. Okay, the second algorithm in Truss Library is reductions. Reductions uses a binary operation to reduce an input sequence to a single value. And some of the operations are sum of an array of numbers, as I told you in the previous session, sum of an array of numbers, or maximum of an array of numbers, maximum of an array, or minimum of an array. Truss reduced is the function for reduction operations. This is the function for here. This command do a parallel reduction to sum all of the elements of an array. It has 4 parameters: beginning of the numbers, sequence of numbers, and end of the sequence of numbers, the initial value of output, and the operator. Operator is addition here, as you see. This is the type of operation, and this is the initial value. These are also does the same job here in default here. If you don't set the fourth parameter, it is summation in default. So this is also performs summation operation. If you don't set the both third and fourth parameters, as you see, Again, this is a summation operation in default. Other reduction algorithms are here, finding the minimum of the smallest element in the range, finding the maximum element in the range, is sorted operation checks the number in the range are in ascending order or not. Countif find the number of elements in the range which satisfy the given predicate. Countif and inner product computes the inner product of two vectors. Third algorithm is prefix sums algorithms. Prefix sums. They perform scan operation. This can be an inclusive scan operation, exclusive scan operation. An inclusive scan operation performs in-place scan, and the default operator is addition here. So it calculates the cumulative summation of the given arrays. Cumulative summation of the given arrays. When we call it, after that we will get this output. So this is the cumulative summation of the given array. So the trans exclusive scan is similar to the inclusive scan, but shifted by one place to the right. Now, when we call exclusive scan, get the similar output with inclusive scan, but here, now they are shifted to right. This part will be in the output here, shifted part, and the first element, the first one is 0 in the output. Okay, the fourth algorithms are reordering algorithms. They perform partitioning and stream compaction operations. Let's look at them here. Copy if function copy the elements that satisfy the given predicate in the first array to the second array. So copy the elements in this first array which satisfy the rule or given predicate to the second array. Partition, reorder elements so that the numbers that satisfy the given predicate precede the numbers that are not satisfied the given predicate. So the satisfying ones will be in the first part of the array, so they are in the first place. Then the remaining ones consist of the numbers that do not satisfy the given predicate. Remove and remove if. Remove the elements from the array which are equal to given value to the given or which does not satisfy the given predicate. And the unique operation, remove the consecutive duplicates of the numbers in the array. And the last algorithms is sorting algorithms. They sort data or reorders data according to the given criterion. Here is the truss sort function. It sorts the elements of the array in ascending order. Here it is the given array, we call it. After running executing sort function, the output is in ascending order. The second function is trust sort by k. So it sorts the k value pairs stored in different arrays. We have two different arrays here, one for here case, the other one is values. We call sort by k, and we sort them according to case, according to this array. but this the order of this array will be same. The permutation will be same. So after calling sort by k, here the permutation of this array and this array will be same. And the third one is stable sort. It sorts the element of the array according to the given comparison operator. Given comparison operator, this one. So the comparison of operator check whether it is greater than the previous one or not. So after running this function, we get this output. The numbers now are in descending form. They are in descending order because of comparison operator, this one, greater comparison operator. Okay. Now continue with CUDA library. CUDA, abbreviated as CUDA, it is coming from CUDA Unbound. It is a generic configurable C++ template library for high-performance CUDA primitives. And it targets each layer of the CUDA programming model. And it has some reusable components, software components. These are parallel primitives, it has parameter primitives and utilities. And this is the website of CUDA, so you can get more detailed information through this website. Let's look at the parallel primitives briefly. If there's three type primitives, the first one is worldwide collective primitives. So it does some operations such as cooperative worldwide prefix scan or worldwide reduction. So it's safely specialized for each underlying CUDA architecture. So it can specialize for any CUDA architecture with worldwide primitives. The second one is block-wide collective primitives. So it does some operations such as cooperative I/O, sort operations, scan operation, reduction, histogram, and etc. for block-wide primitives. And it is compatible with arbitrary thread block size and types. They are compatible with arbitrary thread block size and types. And the third one is device-wide primitives. So these operations can be parallel sort, prefix scan, reduction, histogram, and etc. And it is compatible with the CUDA dynamic parallelism. Okay, let's continue with CUDA's collective primitives. The CUDA's collective primitives allow complex parallel code to be reused rather than re-implemented. So reuse them rather than re-implemented, and allow complex parallel code to be recompiled rather than hand-ported. And the CUDA's collectives are not bound to any particular bit of parallelism or data type. So they are not bound to any data type or number of blocks or so on. So it is adaptable to fit the needs of enclosing kernel computation, and it is trivially tunable to different grain size, such as threads per block, items per thread, etc. So the CUDA is CUDA unbound because of this characteristic. CUDA is CUDA unbound. Okay. why we need CUPS primitive is the answer is here. When writing a kernel code and considering the issues such as deadlock, bottleneck, throughput, shared memory layout, synchronization, granularity, latency, are very challenging and time-consuming process. But the CUPS collectives consider these issues in an efficient way. So you not need to consider these issues by using CUPS collectives. Also, CUPS primitives allow the programmers to determine the proper value of parameters of the kernel easily in order to use the processor resources of the GPU efficiently. So it allows the programmers to determine the parameters of the kernel easily by considering the processor resources of the GPU. And in addition, the programmers do not need to write a kernel code for the different case of particular operations such as reduction scan. When you want to make when you want to add the new cases to these operations, you don't need to write a new kernel code. So CUPS allows you to uh, use such cases without implementing it again. So just using the template of CUPS primitive is enough in this case. You don't need to write the kernel code again for each different case. An example here, a code snippet of device parallel reduction here. We have a device variable, input variable here, and output variable here, and the number of items is 7. We allocate, and we want to make reduction over this device array, given device array, and we need some temporary data structure here, a pointer and a variable. We call some reduction function to determine the storage requirement of these variables. Then we allocate a place for these variables in the device memory. Then we do the some operation by calling this function of CUPS primitive sum divides reduce sum. So the reduce operation performs here, and the output is 38. I will use this function when comparing the three reduction algorithm on the following slides. So I will use this one. Okay, let's compare CUP and Trust. Both libraries provide device primitives for programmers. Moreover, CUP provides single instruction, multiple thread, block-wide, and work-wide primitives. And on the other hand, Trust is not CUDA specific. That means it does not allow the programmers to interfere CUDA specific details, such as the number of threads or streams and etc. So the programmers cannot interfere with the CUDA specific details. Because of that, the primitives of the Trust cannot be configured for a specific GPU architecture. You cannot configure it. But CUP is CUDA C++ specific. It allows the programmers to interfere with CUDA specific details, the number of threads, and the stream parameters. So the primitive CUP primitives can be configured for a specific GPU architecture. Okay, let's continue with the comparison of three parallel reduction algorithm. Just a minute. Okay. Uh, okay, I will compare three different approach. One is efficient parallel reduction proposed by Marquez, and the truss reduce function, and the cup device reduce function. And I used the Tesla K40 board in the experiments, and the number of elements is around 4 million to over 22, and we measure the execution times of reduced kernels or reduced functions of these libraries, measure the execution time of the kernels or reduced functions, and the result is here. The parallel reduction proposed by Paris is 0.147 milliseconds. For Truss Library, 0.49 millisecond, and Cup Library, 0.125 millisecond. As you see that, the Truss has the worst execution time. Cup is a little bit better than parallel reduction, but not too much. Okay, let's compare these three parallel reduction algorithm. Truss has the worst execution time because it does not consider the resources of the specific GPU architecture. It does, and CUDA specific details. It does not allow the programmers to define the number of blocks, number of threads, and etc. And does not consider GPU architectures, the limitations of the GPU. So it has the worst execution time. And also, furthermore, we cannot modify the implementation of the reduction in trust as we needed. So it is hard to improve the performance of a trust function. On the other hand, parallel reduction by Harris and Karp have similar execution time uh, because they consider the specific GPU hardware and the CUDA specific details. And with the parallel reduction algorithm of Harris, we can implement our parallel reduction method by using CUDA built-in functions and APIs. Okay, we don't need to a third-party library. Just using CUDA built-in functions and APIs, we can implement our parallel reduction code. And so we can modify our implementation easily. We can modify our implementation easily when we need to replace the operation in the reduced process. Here, when it is summation, a plus operator, sometimes a minus, sometimes comparison operator, and many other if it is applicable. So we can replace the operation easily, and we can add new parameters to the algorithm easily, and we can improve the performance of algorithm easily, or we can adapt our implementation to the new architectures in the future. So it is also important. But in CUP, of course, the CUP is an open source library, but it is hard to modify the functions in the library of CUP because understanding and examining the codes of someone else are a challenging process. It's a challenging process, so writing your own implementation is always the better choice. And furthermore, CAP collectives do not suggest re-implementing the parallel code. They are not suggest re-implement. They suggest recompile, rerun, but not re-implement. So it is better to run your own code with the built-in functions, CUDA built-in functions and APIs. I want to show you some modification for your code here. The parallel reduction by arrays. This is the original one that I told you. The elements are summed over the block here, or the summation is executed. If you want to find the maximum of an element in an array, assume all the elements in the array are greater than 0. If you want to find the maximum one here, you can just replace this addition with an if structure and put a condition here. So now our code become a reduction that finds the maximum of an element. So we can easily update it here or modify it. Here again, we can add new parameters here. For example, for the maximum operation, while we are trying to find the maximum one, we also want to carry the another information that are related to the maximum one. For example, the main array, this one, GI data, is our main array. We are trying to find the maximum of this array. And the other three arrays, GI data, related one, related to unrelated array, are also device arrays and are related with the main array. So we also want to carry this information along with the maximum one. So here we do the same assignment here inside the if is enough to carry them, and at the end when they are returned to the output arrays here, we also write them to the global memory out as an output here. So we can do it easily, but maybe with Trust or CAP it may be difficult. With Trust is impossible, I think. Not impossible, but it is very hard with Trust, and also I think it is hard with CAPs to such modifications. These are some Coda libraries. Here, Cubulus is used for implementation of basic linear algebra subprograms on CUDA. QSparse, a set of basic linear algebra subroutines used for handling sparse matrices. QRand is an API for generation of high-quality pseudo-random or quasi-random numbers. QSolver provides LAPEC-like features such as common matrix factorization. QFFT, a CUDA fast Fourier transform library, and so on. The others are NVGPIC, MPP, QTensor, QParsalT, and NVGPIC 2000. So this is the website of these Coda libraries, and you can get more detailed information through this website. Okay, before starting remaining issue, okay, let's a 10-minute break, then continue. Okay, let's continue with the remaining issues. I will tell you some important issues in this section. Okay, can you see the slides clearly?
Yes, we can see the slides.
Okay, thank you. Okay, sweet. Okay, let's start with the first issue is the usage of CUDA memset function. And this is the here prototype of using CUDA memset function. It takes a device array and the number that will be set to that array, and the count is the number of bytes that will be set to the given volume. Here we have a small example. Here we have a device array and we allocate a memory in the device. So it will have 3 elements here. We allocate 12 bytes in the memory. Then we set 0 to each element of A. Here the third parameter is the size of count, which is here 12 bytes. So all of the elements of A will be 0. And we call the kernel here with one block and one thread. And here this is our kernel. We print each value of array A here to the screen, and we get 0. So how can we set all the elements of the array to 5? Now we set 0. How can we set 5? Here CUDA map set a GPU. The given value is 5 and the number of bytes is 12. So is this correct? Can we set 5, set the elements of A to 5 with this command? Is this correct? No, this is not correct. We cannot set 5. So in this case, the output is here, the first element, the value of first element, second element, and the third element. The output is very different. So let's try to find and fix how we set the element to 5. Here it has 12 bytes, as I told you. Here we could allocate 12 bytes. First 4 bytes is used for the first element. Second 4 bytes is used for second element, and the fourth byte is used for the third element. So and each location has 1 byte. And with this command, by executing with this command, all of the bytes will be 5. All of the bytes. Since we have 12 bytes, all of them will be 5. So we get this output. So in order to get the correct output, the memory should be initialized like this, or should be set like this. Here, in order to set to any element, the first byte should be 5. The remaining bytes, the remaining 3 bytes should be 0. And again, for the second one, the first byte should be 5, and the remaining 3 of them should be 0. And for the last one, the first byte is 5, and the remaining ones should be 0. In this case, we set each element to 5. So how can we do it? By writing the code here. there are many ways, of course. I will show two of them. At the beginning, in the first way, at the beginning, we set 0 to all bytes. So all of the elements are 0. Then we can add to the add 5. We can set 5 to the first elements of first byte of each element. Sorry, first byte of each element. Here we are accessing to the first. By the way, can you see the cursor clearly?
Yes.
Okay, thank you very much. Okay, uh, uh, okay, let's. Now we are accessing to the. We are trying to set 5 to the first byte of first element. Here, set 5, 1 byte. Then we access to the second element, address of second element, and we set 5 to the first 1 byte, and we access to the third element, and we set 5 to the first byte of third element. This is the first way, and this is the second way. Again, we set all zeros, all of the bytes. Now, by casting the address of array to the car array, we are accessing to the address value as a value, and then we add 0 byte to this address for the first element, we add 0 byte for the second element, and we add 0 byte to the third element, address of third element. So now we are accessing to the first element of each first byte of each elements. So we set 5 and this only for 1 byte. Again, we set 5 to the first byte of each element. Now we set all of the elements to 5 here. Okay, so let's continue with another example. How can we set the first element to 300? Now the question is, how can we set the first element to 300? We are now focusing to the first element. Each 1 byte consists of 8 bits. Okay, can we do this operation with this command? Here, a GPU, the value is 300, and we set 1 byte here. Is this correct? No. Again, we get 44 as the output. So how can we set 300 to the first element of a GPU? Here again, at most 2 over 80, 2 over 8 value can be kept in each memory location. In the first byte, in the first memory location here, the numbers between 0 and 2 over 8 minus 1 are stored. In the second location, in the second byte, the numbers between 2 over 8 and 2 over 16 minus 2 over 8 here. And in the third byte, the numbers between 2 over 16 and 2 over 24 minus 2 over 16 are stored. And in the last byte, in the fourth byte, the numbers between 2 over 24 and 2 over 32 minus 2 over 24 are stored here. Okay. This is important. Okay, let's look at one way to set 300 to the first element. So here the first byte should be 44 and the second byte should be 1. So how can we the remaining ones should be 0. So if we set these values to these bytes, we will get 300 for the first element of A. Okay, how can we calculate it? I would like to show you here. This is our code. We set O0 at the beginning. Then here to the first byte, we are trying to access to the first byte of A here, and we set 44. This is 1 byte, so we set 44 to the 1 byte starting from first byte. Then we are accessing to the second byte of the first element of the array, second byte, and we set 1 to here. Okay, and we can achieve the corresponding value by multiplying 2 over 0 with 44 plus 2 over 8 times 1 will give us 300. Of course, there are remaining parts I skipped here. 2 over 16 times 0 plus 2 over 24 times 0, and it will give us 300. We can calculate the actual value with this approach. So it is important. When we set these values, we get 300 for the first element of A. Okay. Sorry. Okay, now there's an example here. Assume that the first byte of the first element is 100, the second byte of first element is 10, the third byte of first element is 0, the fourth byte of first element is 0. So what is the value of A0 here? Think about that and trying to find the proper output of A. So I will let you for a while to compute the corresponding value of A. What is the output of A0 here? Okay, so here I think all of you completed the output. Okay, why I cannot continue? Okay. Oops. Okay. So this is the code of this example, and we set 100 to the first byte of the first element and 10 the second byte of the first element. So with this formula here, 2 over 0 times 100 plus 2 over 8 times 10, we will get 2660 as the value of first element. Okay. Let's continue with the second issue. So setting up the initial state takes too much time in random number generators. What I mean here, for example, we have a kernel named current init kernel. We have three device variable A again, as in vector addition. We have variable N for random number generator, and we have clock here. And for each thread, we calculate global thread ID. And here, we define a state for the generator, and we initialize the state here by using clock as the seed, thread ID as the sequence 0, and the state variable we call current init inside the kernel for each thread. Okay, then we call current function to generate a random number and assigning to an index. Then we read the value of A and B randomly from the global memory. Okay, we initialize the state inside the kernel. Our data size is 2 over 22, and we have host arrays, 3 host array, 3 device arrays. We set the number of blocks 1024, and we set the number of threads. Sorry, 1024, and we set the number of blocks as the size is divided by 1024, and we get the value from clock in order to use in seed, and we call CUDA event record to calculate the execution time. And here inside the for loop, we call kernel at each iteration of the for loop. Then we copy the output to the host here. So we call 10 times this kernel 10 times. So at each time, each thread in the kernel do an initialization operation for the state. So we call 10 times, and each thread performs initialization of the state 10 times. So in this case, the execution time is 285 seconds. For a vector addition, for a random access vector addition, 285 seconds is very huge. It is not an applicable for the real-time applications. So how we can overcome? Well, I will show you some one of the solution here. rather than initializing the state of the random number generator in a kernel, inside the kernel 10 times, we can initialize the states of the random number generator only once, then we can store their parameters to the global memory as a coalesce way. Then when we need the current value of state, we can read it from the global memory as a coalesce way. I will show you this approach here. Now we are not initialize the current inside the current init kernel. Let's not initialize it. Here we define another kernel, initialize RNG kernel. It initializes the state of the random number generator only once, and then save its parameters, save the parameters of the state to the global memory. I will show you how it does to the global memory here. So before running for loop, we have already initialized the states of the random number generators. Then we send them to our kernel, main kernel, as a random number generator, okay, to a current init here. Then in order to use the state, we load the parameters of the state here as a coalesce way, and use this state to generate a random number and do vector addition. After that, we save the current value, latest value of the state to the global memory again as a coalesce way. Okay, so at each run of current init, we load state as a coalesce way and use it and save it as a coalesce way. So this is important. So we only initialize it only once at the beginning, rather than initialize the states inside the kernel and calling them at each iteration of for loop. So in this case, let's look at performance here. In this case, the execution time will reduce to 28 seconds. So for the same operation, the execution time reduces to 28 seconds, so 10x speed up with this approach. This is important. Maybe if the number of iterations were 1, the execution time of both approach would be similar. But here it is reiterated 10 times, so we do not initialize at each iteration. Maybe we can increase the number of iteration for example, for 400 iteration or 4,000 iteration. So this volume will be very huge. So if we increase the number of iterations 100 times, this volume increases at 100 times. That means it is 28,000 seconds, around 28,000 seconds. So be careful with this one, with this issue. Okay, did I miss anything? Okay. Okay, these are the states of the parameters of the states of random number generator. So these are we are getting the current value of the parameters of the state here to our global variables. We load the latest value of the state from the global memory as a goes way. In here, we store the latest value of state to our global variable here. These are the parameters of state of the random number generator. Okay, let's continue with the L1 cache use in Tesla K40 board. It is in disable mode in default. So the L1 cache is disabled in default. In order to enable the L1 cache use, you need to enter these flags. Okay, so and the size of L1 cache is 16 kilobyte in default. And for the experiment, remember our memory coalesced access example. We have three configurations in that. Fully coalesced, now I call it semi-coalesced access with one segment in each group. This is same with the fully coalesced. And the non-coalesced access, the global load operations performs at most 32 transactions. In semi-coalesced access, where the group's number of segments in a group is 16, the global load operations perform at most 16 transactions. And the third one is fully coalesced, one segment in each group. So the global load operations performs at most one transaction. So with this semi-coalesced access approach, we generate a random number to get the group. We select a random group, and we are trying to get the elements of that group randomly in our example. So now we will investigate the L1 cache use of these three approach. Here, and we use L1 cache global hit rate metric. This gives us the hit rate in L1 cache for global loads. Hit rate means the successful hits. Hit rate means the successful hits. When you want to request when you request a data in L1 cache, if it exists in there, so that is a hit rate. That's the successful hit. If you cannot find, that is not a hit rate. So, for example, if the hit rate is 90, that means 9 of 10 hits are successful. That means 9 of 10 data requests will be successful, and 9 data retrieve or 9 of the 10 data retrievals are successful. Let's look at the in this table. This is the approach. This is full coalesced, semi-coalesced, 16 segments in a group, and non-coalesced. And the number of particles, this is 2 over 15, 2 over 20, and 2 over 23. And these are the execution times. And the execution time of full coalesced, when the cache is disabled, the execution time of the second one approach, and the non-coalesced here. These are the execution times of algorithms when the cache is enabled, and this is the hit rate of cache here. Okay. Let's try to examine this table. When we look at the fully coalesced, that means the global load operations performs at most one transaction. When the cache is enabled, the hit rate is 80.89% here. As the number of particles increases, the hit rate here remains same. So why it is, remains same at around 90%? Because in in fully coalesced approach, only one segment is used and the values are accessed through that a single segment. So since since 128 bytes are stored in L1 cache for a verb has 32 elements, so it is 128 bytes. So and the verb performs a memory operation in one transaction. So 128 bytes are stored L1 cache for a verb. And we have at most 64 verbs in an SM at a time. Since at most 64 verbs can be active in an SM. So at most 8,192 bytes can be stored in L1 cache for the first approach, for the fully coalesced full access. Okay. I would like to repeat here again because important. Since the group consists of one segment, or semi-one, I told you. Since the group consists of one segment, that means 128 bytes. So a verb access to a one segment, so 128 bytes will be stored in L1 cache for a verb. Since at most 64 verbs can be active in a streaming multiprocessor, at most 8,192 bytes can be stored in L1 cache. Since the size of L1 cache is around 16,000, so L1 cache is enough for any number of particles in the first approach. The L1 cache is enough for any number of particles. And 90% hit rate means 9 of 10 hits are successful. But for the other approaches, the semi-16 and for the non-coalesced access, hit rate here, as you see, is very low, and they decreases as the number of particles increases, because L1 cache is not enough to store all the requested data of all active verbs in these approaches, because the verbs can access different segments. So all of the segments cannot be stored in L1 cache. And the execution time of first approach increases because of the high rate. Here, as you see that when the cache is enabled, but for the other approaches, the execution times become worse because of the cache miss ratio. Since hit rate is very small, the cost of the cache miss ratio is very high. Because of that, the execution times become worse for the other approaches. Okay, and these are the references of this session. And let me check the time. We have 50 minutes. Oops. Okay. Okay. Oops. Okay. Let me share the screen. Okay, let's continue with our last session. In this session, before starting our session, I would like to remind the specification of the Tesla K40 board. We will also use these specifications in the following slides. Okay, in this session, I will show you one of the work that we did in the past, which is memory coasting implementation of Metropolis resampling algorithm. And I will show you our proposed flawless variants of our Metropolis resampling, which are Metropolis C1 and Metropolis C2, and we investigate them in terms of global memory load transaction. I will compare them in terms of this metric, and I will also compare their performance in terms of bias and mean square error performance and the tracking performance. And this is the citation of our work. And this work covers most of the issues that I taught you today. First I will give you a brief information about the particle filter and its resampling stage. And I will show you the, the stage of Metropolis resampling and the non-coalesced global memory access problem of the Metropolis resampling. And I will tell you our proposed method, Metropolis C1 and Metropolis C2 resampling techniques that eliminates the non-coalesced global memory access problem of the Metropolis. And then I will show you the experimental result. Okay, the particle filter is a serial Monte Carlo estimation method. Where the system of measurement model is highly nonlinear and the uncertainties are large. The posterior density function approximated by randomly chosen particles along with their likelihood weights. And due to have many particles, its computational cost is very high, but the GPUs offer promising solutions for the particle filter. This is an illustration, and this is a 2D position of a plane here. The number of particles is 64 here. Each color set represents a particle set for a particular time. Okay, here this is the zoom version of it. As you see that the different color sets is the particle set for the corresponding time, and the weighted of these particles, the circles are particles, the weighted average of these particles is the estimation of the target. And the most well-known SI particle filter is the sampling importance resampling particle filter. It has mainly four stages here. In this algorithm here, in the first stage, n is the number of particles, x are the state of the particle, k. W tilde k is the weight of particles, and in the first stage, inside the for loop, we create particle here by using the characteristic of the application. We create particles, then we calculate their calculations for n particles. We do this one. Then the sum of the weights of particles are sum here. Then in the third stage, the weights of each particle normalized by using the sum, and we get the normalized weight of each particle here, n is the number of particles. And in the fourth stage, a resampling operation will be performed. I will tell you why we need resample. Okay, and here zk is the measurement of the sensor, and so on. Why we need resampling? As time progresses, the normalized weight of one particle becomes near to 1, the others become nearly 0. That means one of the particles is very close to the measurement in the following time steps, and the others are very far away from the measurement. So only the one particle will be active. So this causes a degeneracy problem. Only one particle is active, so the others causes wasted effort for our algorithm. So one of the effective solution of degeneracy problem is resampling. In resampling, the particles with higher weights are replicated. The good ones are replicated. It means those with lower weights are eliminated. And this is the metric here is the expected number of replication of ith particle after resampling. This is the expected replication of ith particle after resampling. So we are with resampling algorithms, we are trying to achieve these values. Our target is to achieve such values. So achieving this value perfectly ensures unbiased result, but it is not possible in practice because of random number generators and some numerical issues. Okay, let's go back to the SIR particle filter again. Let's look at in terms of GPU implementation. Since there are no dependency between the iteration of the first loop here in the first step, we can run this loop fully parallel on the GPU. We can create a thread for each iteration of the loop. For the second stage, there is a sum operation, so we can use an efficient parallel reduction in order to get the sum of the weights here. So this is also applicable for GPU. In the third stage, there are no dependency between the iteration of the for loop. So we can run the third stage fully parallel on the GPU. So we can create a thread for each weight. And in the third stage, again, we calculate the estimation of the target here by summing these multiplications. So we can use an efficient parallel reduction again. For the fourth stage, resampling, I will tell you on the following slide the implementation of the resampling stage. Okay, this is the well-known resampling method, one of the well-known resampling methods, systematic resampling for the fourth stage. Okay, systematic resampling, but it encounters such problems. For example, here let's look at this algorithm. There is an here inclusive prefix sum operation. We can use parallel scan algorithm here, but since all of the weights are interact each other, this causes a less radicalization. The for each the interaction there is no dependency between the iteration of the for each loop here. So each thread can run in parallel on the GPU. This part is okay, but another problem is numerical instability problem. That means by adding very small number u is between 0 and 1, as you see. When the number of particles is very large, for example, n is the number of particles. When it is very large, for example, 1 million, 4 million particles, so R will be very large. So when by adding u very small number to a very large number causes a numerical instability problem because there is no effect on the result when adding very small number to a large number. So this causes numerical instability problem. So it has two problems. One of them is numerical instability, though the second one is the interaction of all weights causes less radicalization. In order to overcome this problem, Murray and his co-workers proposed Metropolitan resampling algorithm. Let's focus to this algorithm. Look at this one here. There is a loop here, and there is no dependency between the iteration of the for loop. So each thread can run this one in parallel. And rather than using all of the weights in this algorithm, the Metropolitan resampling use only the ratio of two weights. So there is no collective operation here, just ratio of two weights here, which is also important. And B is the trade-off parameter for Metropolis between speed and bias. But here, Metropolis resampling faced with another problem. Since the weights are loaded in a random fashion here, we create a random number between 1 and n for j inside the inner for loop. We generate a random number, random index for j, and read weight from the global memory as a non-coalesced way. For the threads in the same warp, read this one as a non-coalesced way. So this operation causes non-coalesced global memory access pattern for the Metropolis resampling. And we will propose two techniques to overcome this problem. Global memory, as I told you before, global memory consists of consecutive segments, and the memory operations perform segment by segment through global memory. So when a warp tries to load a value from the global memory, if the threads in the warp access to the different segments of the global memory, that operations will become serial. So this is important, as I told you before. So what is our before that one? This is the global access pattern to the global memory of Metropolis resampling. As you see that the threads in the world access to the different segments of the global memory. So this causes now called global memory access patterns for Metropolis resampling. Our approach is trying to force the threads in the same world access to the same segment of the global memory. To do this, or to make this generic, we define an S segment concept here. A segment consists of contiguous real segments. Okay, a segment, we define a segment concept. Like grouping, it consists of contiguous real segments. Here, the smallest S segment consists of a single segment, as you see. The smallest S segment consists of single segment, real segments, and the largest S segment consists of whole segments in the device array. Okay, the largest S segment here consists of the whole segment in our definition. Okay, let's continue our first approach, which is Metropolis C1 resampling. In here, we are focusing on this part. Just a minute. Here, this one. We are focusing this one and try to eliminate the problem here. Now the index are between 1 and n, and when we read double j, it may be in any segment, and our focus to this part or in the solutions here. So in the first technique, we did, as I told you before, we define a segment. So in the first one, before the inner loop, we select an S segment only once time. Okay, we select an S segment here. We can define size, by the way, and we select a random index within this S segment. We select a random index within this S segment for each iteration of the for loop. For each iteration of the for loop. So when we read the WJ, the threads in the same world read the WJ from the same S segment. From the same S segment, okay? For the second approach, here we select an S segment at each iteration of the for loop. At each iteration of for loop, we select an S segment and we select a random index between or between this selected S segment here. Again, when we read WJ at that iteration, the threads in the same work access to the same S segment. Same S segment. But in the second approach, we select a new S segment at each iteration. So this will improve the performance because in the first approach, since we select only a segment only once, we read the weights from a limited portion of the array inside the for loop. At each iteration of for loop, we read the weights from the same S segment, so very limited portion. For the small, when the size of S segment is very small, we only access to the very small portion of the data. This is not a good thing for us. But for the second approach, at each iteration, since we select an S segment at each iteration, we can access to the different segments inside the for loop. So this directly affects the reading of WJ, but indirectly, this approach indirectly affects the reading WT. In here, WT also will be from the selected S segment before the for loop in C1, but in C2, WT also depends on the previous selected S segments. Okay, so this also affects indirectly to read WT. Okay, and this is our experimental environment. We use this formula to create our weights. Okay, and we take Y to 4 and we create 16 different weight sets and run them 256 times and get their average to obtain the output. And we use CUDA profiler, GRD transaction per request metric we use, and this matrix gives us the average number of global memory load transactions performed for each global memory load. Sorry. And this number will be in between 1 and 32, as I told you before. At most, we can at most 32 transactions performed for a hop. So the average number will be between 1 and 32. Okay, let's focus to the Metropolitan C1 at first. When the S segment size is 128 kilobyte, here, that means the S segment consists of single segment. So WJ is loaded in one transaction for C1 and C2, okay? Because the S segment consists of one segment. In when the S segment size is 2048 kilobyte, that means S segment consists of 16 contiguous real segments. 16. So WJ is loaded at most 16 transactions for C1 and C2. WJ is loaded at most 16 transactions. For WT, when the segment size is 128, WT is loaded at most 2 transactions for C1. The first one is coming from the selected segment. The second segment, at most 2 transactions means it may access at most 2 different segments. So one of them is coming from selected S segment. Second one is coming from the initial value of T here. So this is also another segment. This is this index is of another segment. Okay. Sorry. So at most WT is loaded at most at 2 transactions for C1. And WT, when the S segment size is 2048 kilobyte, WT is loaded at most 17 transactions for C1. 16 of them coming from the selected S segment. One of them is coming from the initial value of T. So at most it can access at most 17 different segments, so 17 different transactions for C1. For C2, and the segment size is 128, a segment consists of one segment. So WJ is loaded in one transaction for C2. When the segment size is 2048 kilobyte, a segment consists of 16 contiguous segments. So WJ is loaded at most 16 transactions for C2. For WT, when a segment size is 128, that means a segment consists of a single segment. But when reading WT here, since WT depends on all of the selected segments in the past, so the values of WT depends on all of the selected segments in the past. So it is loaded at most 32 transactions. So there may be more than 32 different segments in the past inside the selected segment. So WT is loaded at most 32 transactions. Again, when the S segment size is 2048 kilobyte, the S segment consists of 16 contiguous segments. So the reading WT at most 32 transactions for C2 because WT, the value of WT depends on all of the selected S segments in the past. Okay, let's look at the global load memory, average global load memory of the 5 techniques, 5 methods here. Here, this is the summary of the maximum number of transactions for the reading of these parameters for each configuration. Here, for example, when this is the size of S segment, this is the size of N segment. Here, this is a summary of it. So we achieved the best result with Metropolis C1 when the S segment size is 128 because WJ is loaded at most 1 transaction, WT is loaded at most 2 transactions. So the average is 1.5. It cannot exit 2, cannot be lower than 1, cannot exit 2. So this is the output of GLD transaction broadcast here, the best output of the experiment. And for the second approach, C2, where the segment size is 128, WJ is loaded at most 1 transaction, WT is loaded at most 32 transactions. So here so the red one is the result of this one is around 9. But for the following one, when the Metropolis C1, where the segment size is 2048, WJ is loaded around 16, WT is loaded around 70. So the output is around here, around 13 for this approach. For the fourth approach, WJ is loaded at most 16 at most, be careful, and WT is loaded at most 32. So here the purple one is the output of the metric around 22, and the black one is the result of original Metropolis, and we know that it is around 32, result of metric. So the order of these results are compatible with this table, as you see. Yes, in this example, we learned that the non-coalesced access patterns have direct effects on the execution time. But it is not the only reason for the execution time of the application. Also, hardware resources and limitations can affect the execution time. These are size of L1, L2 caches, or the number of cores, or the maximum number of threads that can be active at a time. All of them have effect on the execution time, or the number of particles also affects on the execution time. And this is the speed up result of our proposed techniques here. We achieve up to 10x speed up with our proposed methods for the very large number of particles. This is the L1 cache use here. We use same metric here, and the values in the table is the L1 cache global loads hit ratio of the algorithms in terms of percentage. And this is the size of cache. These are the number of particles. These are the abbreviation of the kernel algorithms. This is Metropolis algorithm. Metropolis C1 with a segment size is 128 bytes. Metropolis C2 with the corresponding segment size, and so on. And then here the values that are underlined means the original algorithm runs faster than its cache version. That means when we enable the cache, the execution times becomes worse for the values that are underlined. Okay, if it is not underlined, the cache version of the approaches are better than the non-cache version. So in here, as you see that in all of the number of particles, Metropolis C1 with a segment size is 128 have always achieved a better hit ratio here, around 96%. 96%, as you see that. And all of its configurations and in all of the particle size, the execution time improves when the L1 cache is enabled. And we get high ratio for each number of particles because the data, the number of data is enough for the size of cache. So we can store all of the data in this configuration in L1 cache. It is enough to store all of the segments read by verbs to the L1 cache. So we get these high ratios. But for the other ones, the hit ratios reduces as expected. So we benefit from L1 cache with Metropolis C1, where the S segment size is 128. And these are the bias and mean square results of algorithm here. Let's focus to the here. This is the original Metropolis algorithm, and this is Metropolis C1, where the segment size is 128. As you see, the bias become worse here with C1 because the A segment consists of one segment, so we have a limited portion of data, and we select the weights within that data, so bias will increase dramatically. But for the Metropolis C2, where this S segment size is 128, we achieve similar bias with the original Metropolis Resounding, because even if the S segment size, even if the S segment consists of one segment, we select a new S segment at each iteration of the for loop. Because of that, we access to the different segments at each iteration, so we achieve similar bias with the original Metropolis. But when we compare the mean square error here, the original Metropolis is here obtained around 1, and the mean square error of Metropolis C1 is worse than the original because of the bad bias results. But for the Metropolis C2, it is better than C1, but worse than Metropolis because of some variance on the result, not the bias, variance. So, but this is not important here, as you see. So with Metropolis C2, we can implement our algorithms if we want to have a faster result than the original one. And for the other configuration, where the S segment size is 2048, as you see that a bias of C1 becomes better than the previous one because the number of segments in S segment increases. Now the S segment consists of 16 segments, so the bias of C1 becomes better. But the bias of Metropolis becomes same because we have already achieved the expected bias, so it does not affect the bias result. But when we examine the mean square error results, as you see that the mean square of C1 also improves because the bias of C1 improves. And as you see that the variance of C2 now improves. So here around 1, it is around 1, it achieves to the same mean square error with Metropolis, along with better execution time than the Metropolis. Okay, and this is the effect of S segment size, and as the S segment size increases, both C1 and C2 approach to Metropolis. What they mean? When the S segment size is equal to 4n, that means S segment consists of all contiguous segments, so both C1 and C2 become same with Metropolis resampling. So with a segment size, we provide a trade-off between speed and quality. And at the end, I would like to show the tracking performance briefly. This is a plane in 2D dimension, and its states are x position, y position, velocity in x position, and velocity in y position. And we use nearly constant velocity model on the system model. Now we generate particles to this model. And for the measurement, we use range and bearing of the target from the radar. And this is the execution time ratios of each stage of the particle filter. We have fourth stage. Remember that the fourth stage is resounding, and these are the percentage of this stage to the total execution time. Here, when the number of particles is 2 over 14, the resampling stage, the ratio of resampling stage to the total execution time is 71. Okay, and for the C1, S segment size is 128. The ratio of resampling is 55 to the total execution time. For the C2, where S segment size is 128, the ratio of execution time of stage 4 to the total execution time is 60%. When we check the result where the number of particles is 2 over 22, as you see that the ratio of execution times of stage 4 to the total execution time is 95. This is very huge. Okay, but with our proposed methods, the C1, the execution time of C1 to the ratio of the execution time of the C1 to the total execution time is 72.87. It's around 72, and the ratio of total execution time of C2 to the total execution time is 85%. So when we check the total execution times, you see that the original Metropolis achieves 25 seconds here, but the execution time of C1 with SS is equal to 128 is around 3.7 seconds. This is very important here. And here the total execution time of C2 is around 7 seconds. So improving the performance of resampling stage is very important, as you see in our study. Okay, and these are the quality result, the root mean square result of the target of our filter. Sorry. So as you see that this metric is root mean square error metric, and it's calculated with this formula, and we get this results for the different number of particles. These are the number of particles, these are the configuration of the algorithms, and Metropolis and C1, C2 of all configuration, and C1 with SS 2048 achieves the similar root mean square error, but the root mean square error of C1 with SS is equal to 128 is a little bit worse than the other ones, but it's not a substantial difference for the tracking applications. So this is also acceptable result for us. So we can choose one of them. Of course, it is better to choose the fastest one. Okay, and these are the references of this session. Okay, just I would like to check the question and answer section. I think there is no question here. Okay, and you can ask any questions related to this training or any issues about these topics at any time as you wish. And I would like to thank you for attending our trainings both yesterday and today. I also want to thank to Mrs. Zamsar and Mrs. Maria Demirtaş for their valuable supports.
So
Okay.
we can end the webinar now, right?
Yes.
So thank you so much for your contribution, and thank you all for attending. See you at the next event. Have a nice day. Bye.
Thank you very much. Have a nice day.